Hey everyone, my name is Brad Tran, and today I'm presenting a paper called EcoFuzz, Adaptive Energy Saving Greybox Fuzzing as a variant of the adversarial multi-armed bandit. This was published at SEC'20 2020 by a team from the National University of Defense Technology in China, led by Tai Yu. The title is dense, but we're going to break it down piece by piece. By the end of this, you will understand what every word in that title means and why it matters for how we approach vulnerability discovery. So here's our roadmap. We'll start with some background on coverage-based graybox fuzzing and how AFL works, just enough to set up the problem. Then we'll look at why AFL's scheduling algorithm is fundamentally inefficient and what prior work tried to do about it. After that, we'll get into the theoretical core of the paper. The authors model fuzzing as a variant of the multi-armed bandit problem from game theory, which I think is the most interesting contribution. Then we'll see how they implement that theory into a tool called EcoFuzz. And finally, we'll evaluate the results and discuss some limitations I identified. Let's get into it. So we all know fuzzing at a high level. It's automated software testing through generating inputs and monitoring for anomalous behavior like crashes, hangs, or memory violations. It's been around since Barton Miller's work in 1989 and has become one of the most practical techniques for finding real security vulnerabilities at scale. What I want to focus on here is the distinction between how fuzzers approach the problem. On the left, you have the core idea, which is to generate inputs, feed them to the target, see what breaks. On the right, the key insight that makes modern fuzzing so effective is if you can observe which code the program actually executes on each input. Then you can use that feedback to guide future input generation toward unexplored regions of the program. To give you a sense of impact, Google's OSS or open source fuzz project has found over 10,000 bugs across more than 1,000 open source projects using this exact approach. This isn't academic theory. This is how the industry actually finds vulnerabilities at scale. Quick review of the three main categories. The first category is black box fuzzing. Black box fuzzing operates with zero knowledge of program internals, purely random input generation. It's easy to deploy, but has no ability to direct testing toward interesting program behavior, so it's inefficient for deep coverage. White box fuzzing sits at the other extreme. Full program analysis through symbolic, execution, and constraint solving. It can reason precisely about which inputs reach which code paths, but the computational overhead makes it impractical for most real-world programs at scale. Lastly, but certainly not least, is the gray box fuzzing. Gray box fuzzing is the middle ground and what this paper focuses on. It uses lightweight coverage instrumentation to observe which code paths each input exercises, then uses that feedback to guide a mutation. You get meaningful intelligence about program behavior without the overhead of full program analysis. This category is formally called coverage-based graybox fuzzing, or CGF for short, and is the most widely adopted CGF is American Fuzzy LOP, AFL. So let me walk through AFL's core loop because understanding it is essential to understanding what EcoFuzz improves. AFL operates in 4 steps. First, it selects a seed from its queue. A seed is a test input that previously triggered interesting behavior, specifically a new code path. Second, it assigns energy to that seed. Energy, in this context, has a very specific meaning. The meaning is that it's the number of mutated test cases that will be generated from that seed in this round. Third, it mutates the seed by applying transformations, bit flips, byte insertions, arithmetic operations, splicing two inputs together, etc. This produces a batch of new test cases. Fourth, it executes each test case against the target program with instrumentation enabled. The feedback loop is the key mechanism here. If any test case triggers a code path that AFL hasn't seen before, that test case gets added to the seed queue as a new seed, and then the cycle repeats. Over time, this builds a corpus of diverse seeds covering more and more of the program's execution space. Two terms that will come up constantly in this paper is that a seed is a test input in the queue, and energy is the number of test cases generated from one seed in one round. The entire paper is about answering two questions more intelligently. Which seed should I pick next, and how much energy should I give it? A bit more detail on how AFL's coverage feedback actually works. At compile time, AFL inserts lightweight instrumentation at every branch point in the target program. At runtime, these probes record which branch transitions or edges were taken during execution. A unique combination of edges defines a unique path. So, if a test case takes a particular sequence of branches that AFL hasn't observed before, that input is considered interesting and gets saved into the seed queue. Why does this matter? There's a well-cited result from Charlie Miller showing that a 1% increase in code coverage corresponds to roughly a 0.92% increase in bugs found. Coverage and bug discovery are strongly correlated, which is why maximizing path coverage is the central optimization target for these fuzzers, and the target that EcoFuzz is designed to optimize. Before we get into the problems of AFL, consider this scenario. You have 24 hours of fuzzing time and thousands of seeds in your queue. Some seeds consistently produce test cases that discover new paths. Others keep exercising the same well-trodden code, no matter how much you mutate them. How would you allocate your limited computational budget across these seeds? That's the core scheduling problem this paper addresses, and this is something to think about as this presentation keeps going. So here are the three fundamental issues with AFL's scheduling. First, constant energy allocation. AFL uses a fixed formula to assign energy based on a seed's performance score, things like execution time, coverage, and discovery time. But it can't adapt based on whether previous rounds of fuzzing that seed were productive. If AFL gives a seed 1,000 test cases and 0 of them find a new path, the next round's allocation doesn't meaningfully reflect that failure. Second, the high frequency path problem. Seeds that exercise common, heavily tested paths receive comparable energy to seeds exercising rare paths. But if a path has already been hit millions of times by other test cases, the marginal probability of discovering something new by hitting it again is essentially 0. AFL doesn't actually distinguish between these cases. Third, naive seed selection. AFL walks through its queue in roughly a sequential order with a simple preference of favored seeds based on execution speed and input length. there's no principled mechanism for identifying which seeds have the highest probability of leading to new path discoveries. The fundamental issue is that AFL scheduling has no theoretical model behind it. The two most important decisions in the fuzzing loop and the seed selection and energy allocation are made without a rigorous framework. The most notable prior attempt to fix this was AFL Fast by Bohm and colleagues in 2017. ALO Fast modeled CGF as a Markov chain, a stochastic process where each state represents a program path, and transition probabilities describe the likelihood of mutating a seed on one path to produce a test case that exercises another path. Using this framework, AFL Fast implemented a monotonous power schedule that assigns less energy to seeds on high-frequency paths, which was quite a real improvement. But AFL Fast had limitations. Its schedule is monotonous. It always adjusts in one direction and can't react to whether its allocations are actually being used efficiently. The Markov chain model also assumes constant transition probabilities, but in reality, the probability of finding new paths decreases over time as the fuzzer explores more of the program. And more fundamentally, the EcoFuzz authors argue that this isn't just probability estimation problem. It's a resource allocation problem with an inherent exploration-exploitation trade-off. That's a game theory problem, and it calls for a game theory framework. The framework is the multi-armed bandit problem, or MAB. For those unfamiliar, the classic formulation goes like this. You have n arms, typically described as slot machines, each with an unknown reward distribution. You have a finite number of plays. Your objective is to maximize total cumulative reward. The challenge is that you don't know which arms are best, so you need to spend some plays gathering information about each arm's payout rate. But every play you spend on information gathering is a play you're not spending on the arm you are currently believe is the best. This is the classic exploration-exploitation trade-off. Formally, the classic MAB assumes two things. The number of arms is constant, and each arm's reward probability is stationary. It doesn't change over time. Now here's the connection to fuzzing. It's natural to map each seed to an arm and each round of mutation and execution to a play. A reward is discovering a new path. But, and this is the key insight, fuzzing violates both assumptions of the classic MAB. The number of seeds increases every time you find a new path, and the reward probabilities decrease over time as more paths get discovered. That's why the authors need a variant of the model. Let me make this trade-off concrete in the fuzzing context. Exploration means allocating energy to seeds you haven't thoroughly tested yet. The goal is to estimate the reward probability, their potential for finding new paths. Some of these seeds might turn out to be highly productive, but you don't know until you invest resources into testing them. Exploitation means selecting seeds with known high reward probability and concentrating your energy there. This maximizes short-term returns because you're working with seeds you've already identified as productive. The risk is that you might miss even better seeds that you never even explored. Neither pure exploration nor pure exploitation is optimal. If you only explore, you waste energy on low-value seeds when you already know where the productive ones are. But if you only exploit, you might get stuck on seeds whose reward probability has attenuated while overlooking fresh seeds with higher potential. The optimal strategy is balancing both, and that balance shifts over the course of the fuzzing campaign. So now that you understand the MAB framework, how would you formally map it to the fuzzing process? What corresponds to an arm? What's a reward? And what does it mean to pull an arm? Think about the mapping, because that's exactly what the authors formalize next. The authors propose VA-MAB, a variant of the adversarial multi-armed bandit. Let me walk through the mapping. Arms map to seeds. Pulling an arm corresponds to mutating a seed and executing the resulting test case. A reward is discovering a new program path. So far, that's a straightforward MAB mapping. But here's where the variant comes in, and this is what makes the paper's contribution novel. In the classic MAB, the number of arms is constant, but in fuzzing, the number of seeds grows because every new path discovery adds a seed to the queue. And in the classic MAB, reward probabilities are stationary, but in fuzzing, they actually decrease. The paper calls this probability attenuation. As more paths are discovered, fewer remain undiscovered, so every seed's probability of finding something similar or finding something new shrinks. These two properties, increasing arms and decreasing reward probabilities, means that the existing MAB algorithms like EXP3, which are designed for the adversarial case but assume a fixed number of arms, cannot be directly applied. The authors need new algorithms tailored to this variant, and that's what EcoFuzz implements. Let me formalize probability attenuation because it's central to the model. The reward probability of seed I, given n discovered paths, is P of Ri, n equals 1 minus the sum of transition probabilities Pij for all discovered paths j from 1 to n. As more paths get discovered, that sum grows, and the reward probability monotonically decreases towards 0. This matches what we observe empirically in fuzzing. Path discovery follows a concave curve. Early in the campaign, new paths are found rapidly. Over time, the rate of discovery slows significantly because the remaining undiscovered paths are harder to reach through random mutation. This diminishing returns pattern is exactly what probability attenuation describes. The practical implication is that scheduling decisions become increasingly consequential as fuzzing progresses. In the early stages, most seeds have reasonable reward probabilities. In the later stages, only a few seeds still have meaningful potential, and wasting energy on the wrong ones is very costly. An effective scheduler needs to account for this dynamic. Based on the VA-MAB model, the authors classify the fuzzing process into 3 states depending on how much information is available about the seeds. The initial state is before any fuzzing even begins. No seeds have been tested, so that means there's no information about reward probabilities. The only option is to actually start testing. The exploration state occurs when some seeds have been fuzzed and some haven't. The priority here is that testing unfuzzed seeds to estimate their potential while being conservative with energy allocation, where you don't want to commit heavy resources to a seed before you have evidence that it's even productive in the first place. The exploitation state occurs when every seed in the queue has been fuzzed at least once. Now you have estimated reward probabilities for all seeds, so the strategy shifts to selecting and prioritizing the most promising ones. Critically, this is a cycle. When a new path is discovered in the exploitation state, a new unfuzzed seed enters the queue, and the fuzzer transitions back to exploration. This cycling continues until timeout. Different strategies are optimal in each state, and EcoFuzz implements state-specific algorithms accordingly. Now let's look at how this all comes together in the actual tool. EcoFuzz is built on AFL 2.52b and follows the same basic feedback loop, but replaces AFL scheduling logic with two new algorithms. The flow is determine the current state, initial exploration, or exploitation. Then select the next seed. In exploration, seeds are chosen in queue order to ensure unfuzzed seeds get tested. In exploitation, seeds are selected using SPEM based on estimated reward probability. Then assign energy using the AAPS algorithm, and finally, mutate and execute as normal. One other important change is that the EcoFuzz disables AFL's deterministic mutation strategies and removes the mechanism where AFL doubles energy when a new path is found. Both of these turn out to actually be counterproductive, as we'll see in the results. Let me walk through SPEM and AAPS individually. SPEM, which stands for the Self-Transition Based Probability Estimation Method, addresses the seed selection problem in the exploitation state. The fundamental challenge is that you can't compute a seed's exact reward probability. That would require knowing the transition probabilities to all undiscovered paths, which depends on the program's path constraints, information that a Greybox fuzzer by definition doesn't have. So the authors use an observable proxy, the self-transition frequency. This is the fraction of test cases generated from seed I that exercise the same path as seed I itself. If self-transition frequency is high, most mutations are producing redundant test cases that don't explore new territory. That seed is likely exhausted. Conversely, low self-transition frequency means the seed produces diverse outputs and has more unexplored potential. The estimation formula is P of R1 approximately equals to 1 minus FII divided by the square root of I. The square root of I factor accounts for probability attenuation. Earlier seeds have had more time for their reachable paths to be discovered by others, so their reward probability has likely attenuated more. The authors acknowledge that this is a qualitative ranking, not a quantitative estimate, but for seed selection, relative ordering is what matters. AAPS, which stands for Adaptive Average Cost-Based Power Schedule, handles the energy allocation. The core concept is average cost, total test cases generated divided by total paths found. This gives you the average number of executions needed to discover one new path at any time in the campaign. AAPS uses this as a dynamic budget baseline. Three principles govern the algorithm. First, in the exploration state, never allocate more energy to a seed than the current average cost. This prevents over-investing in untested seeds. Second, reduce energy for seeds exercising high frequency paths. The algorithm computes a coefficient k based on how frequently a seed's path has been hit relative to the average cost, and scales the energy allocation down accordingly. Third, and this is the adaptive part, AAPS tracks a regret metric. If the fuzzer allocated energy and found a new path early in the round, meaning most of the remaining energy was wasted, the algorithm reduces the global rate parameter for the next allocation. If energy is being used efficiently, the rate holds steady or increases. This is fundamentally different from AFL's constant schedule and AFL Fast's monotonous schedule. EcoFuzz creates a feedback loop in which the scheduler learns from its own efficiency in real time. Before we look at results, given what you know about the model, what metrics do you expect EcoFuzz to excel at? Path coverage, bug finding, energy efficiency? Think about what VAMAB actually optimizes for. So the evaluation is comprehensive. 14 real-world programs, NM, Objective Dump, Read Alpha, TCP Dump, Image Magic, LibArchive, and others. 7 baseline tools include AFL, AFL Fast, AFL Fast.new, Fidgety AFL, FairFuzz, and MOPT AFL. Each experiment ran for 24 hours on a single core, repeated 5 times to account for randomness. Total compute, 490 CPU days. The authors also evaluated on the Lava M benchmark and extended to IoT device testing. So here are the headline numbers and the headline results compared to vanilla AFL. EcoFuzz achieved 214% of AFL's path coverage, more than double, while generating only 68% of AFL's test cases. The average cost, meaning execution per new path discovered, dropped by a whopping 65%. Compared to stronger baselines, such as Fidgety AFL and AFL Fast.new, EcoFuzz found comparable or even greater path coverage while generating roughly 65% of their test cases and reducing average cost by about 33 to 39%. What this means practically is that EcoFuzz gets more coverage out of every execution cycle. The energy that AFL and its variants waste on redundant testing of high-frequency paths, EcoFuzz redirects toward productive exploration. This advantage is especially pronounced in resource-constrained settings like IoT fuzzing through QEMU, where each execution is significantly more expensive. The authors also conducted a detailed analysis of scheduling efficiency on the NM binary. The utilization ratio measures what fraction of allocated energy actually contributed to finding a new path. Closer to 1 means less waste. EcoFuzz's average utilization ratio is 0.121, compared to 0.005 for Fidgety AFL and 0.010 for AFL Fast.new. That's roughly 12 to 24 times more efficient. The effective allocation metric, where the fraction of rounds that found at least one new path, shows a similar pattern, 29% for EcoFuzz versus 1.3% for Fidgety AFL. A significant factor here is AFL's built-in mechanism of doubling energy when a new path is found. The data shows this consistently creates waste. The fuzzer rarely finds additional new paths during the doubled allocation. EcoFuzz removes this mechanism and replaces it with the adaptive regret-based approach, and the efficiency gains are substantial. Beyond path coverage metrics, EcoFuzz demonstrated real vulnerability discovery. 12 vulnerabilities total, 2 assigned CVE numbers. In GNU binutils, EcoFuzz found heap buffer overflows in BFD hash and BFD do print. The latter confirmed as CVE 2019 12972. Notably, one of those bugs was found only by EcoFuzz and not by AFLfast.new, despite AFLfast.new finding more raw crashes in the same binary. More crashes doesn't always mean more bugs, or more unique bugs. On Lava M, EcoFuzz found the most bugs among all tested tools, over 1,400 of the WHO program, including 200 unlisted bugs. The IoT application is also worth highlighting. The authors extended EcoFuzz to Fuzz MikroTik Router OS's SNMP component and found a denial of service vulnerability that was subsequently patched by the vendor. This validates practical value of energy-efficient fuzzing in environments where test case execution is expensive. Before I share my critique, what weaknesses do you see in this approach? Consider the model's assumptions, the empirical parameters, what the tools don't optimize in the evaluation methodology. Take a little bit to think about that. Well, here are the limitations I identified. First, empirical constants without theoretical justification. The coefficient k values 1, 0.5, and 0.25, and the energy upper bound m set to 16 times average cost are described as empirical values. The paper provides no sensitivity analysis showing how performance changes if you adjust these. They may be tuned to these specific benchmarks and might not generalize well. Second, the SPEM estimation is acknowledged by the authors themselves as qualitative rather than quantitative. The square root of I factor for modeling probability attenuation is an intuitive choice, but there is no formal derivation connecting it to the actual dynamics of reward probability decay. A different function, log of I, or I to some power, might perform equally well or better. Third, EcoFuzz ignores execution time entirely when allocating energy. A seed that takes 10 milliseconds to execute gets the same energy budget as one that takes 10 seconds. In terms of wall clock time, that's 1,000 to 1 difference. The paper acknowledges this leads to fewer total executions in some benchmarks, though EcoFuzz compensates through better scheduling quality. Fourth, EcoFuzz only optimizes the scheduling side, seed selection and energy allocation. It doesn't modify mutation strategies at all. FairFuzz and MOPT optimize mutation, but EcoFuzz optimizes scheduling. Combining both seems like an obvious next step, but the paper doesn't evaluate this. The authors mention reinforcement learning as future work, but that hasn't materialized in a follow publication as far as I can tell. Let me close with 5 takeaways. 1. The most important contribution of this paper is the reframing. Fuzzing scheduling is an exploration exploitation problem from game theory, not just a probability estimation problem. That perspective shift opens the door to a large body of existing theory. 2. The VAMAB model gives us a principled framework for understanding AFL's inefficiency. It's not just that AFL is suboptimal. The model explains precisely where and why energy is wasted, specifically in how AFL fails to distinguish between states that call for exploration versus exploitation. 3. Relatively simple adaptive strategies can produce large gains. Average cost baselines and self-transition estimation are complex techniques, but they yield over a 2 times improvement in coverage. 4. 214% path coverage with 32% fewer test cases. The efficiency argument is compelling, and particularly relevant for constrained environments. 5. The VAMAB model is generalizable beyond AFL. Any Greybox fuzzer that has a seed queue and an energy allocation mechanism could potentially benefit from this framework. If you want the full technical details, the paper is available through SEC'20. The source code is on GitHub, and at the bottom of the slide is the link to the conference and the presentation and the paper. Thank you so much.